All right, this is just kind of a hint. Grignards add to esters and acid chlorides to give tertiary alcohols with one group from the ester or acid chloride and two identical groups from the Grignard. All right, formate esters give secondary alcohols with a hydrogen from the ester and two identical groups from the Grignard. So it's basically saying so let's just go back here. You've got an R group from the ester and then two of the same R groups from your Grignard. However, if you use formate, which would be H carbonyl OR, all right, notice you have an H there. So your product is going to be H plus whatever your Grignards are. So a secondary alcohol. That's what that's basically saying. Alkyl cuprates you can add to acid chlorides, and it stops at one equivalent. All right, these reagents are called a Gilman reagent, but you can add these to acid chlorides and it stops once. The organolithiums and the Grignards keep adding to it over and over and over again, but the organocuprates stop, which I believe we've learned already. Grignards to nitriles, same type of thing. You can add a Grignard to a nitrile. It stops at the imine, and then as soon as you acidify, okay, you go to the imine, which then immediately goes to the ketone. It hydrolyzes off the imine. Okay, so nitriles to ketones. All right, synthesis of acid chlorides. We've seen this before. You're basically, sorry, get that out of the way. You are SOCl2. Okay, is the common reagent. Oxalochloride is also a common reagent, but mostly it's SOCl2. Okay, again, they have this written incorrectly, right? This 2 should be on the outside, not on the inside. Okay, because the reagent is this. That's what the reagent is. So that's just an error from the publisher. Okay, so here it is again, a review. This is basically a review. Acid chlorides. Acid chloride plus water gives you carboxylic acid. Alcohol, ester. Amine, amide. Carboxylic acid, anhydride. Okay, acid chloride plus 2 equivalents of Grignards give you the tertiary alcohol. Okay, a Gilman reagent or organolithium gives you the ketone. You can pretty much read this, but sodium borohydride or LAH gives you primary alcohols. You know, they don't really talk about this. I hate when the book does it. They just kind of throw it in there without even saying it. You know, we talked about LAH is so much more reactive with acids and esters. Well, acid chlorides are so reactive that you don't have to have a reactive reagent. Actually, sodium borohydride will work on acid chlorides to form the alcohol. Okay. And then dibal or this terp-butoxide will stop at the aldehyde. Friedel-Crafts acylation. Here's just a reaction with an acid chloride. Just to remind you, this is here. There you go. I think we're done with that. Anhydride synthesis. You know, acid chlorides plus a carboxylic acid plus pyridine. This is pyridine, a proton sponge. We've talked about this. Pyridine is used quite a bit as a base to pluck off the acidic proton that you're going to be forming. All right. So the most generalized method of making anhydrides is the reaction of the acid chloride with the carboxylic acid or the carboxylate salt. All right. Pyridine is sometimes used to deprotonate the acid and form the carboxylate. We've talked about that. It's a proton sponge. So here's reactions with anhydrides. Again, this is just a summary. Water or alcohol or amines to form the corresponding acid, ester, or amide. We haven't talked too much about this, but you can actually take amides like an acid chloride and do a Friedel-Crafts. Don't worry too much about this. This is probably the most interesting reaction, this one right here. Okay, it actually opens up the ring, all right, and you know this carbon's attaching to the ring, and then you're left with a carboxylic acid. That's a pretty interesting reaction, but other than that, we're not really going to talk too much about that. Acetic formic anhydride. These are when you have mixed anhydrides. Okay, what reacts? What's more reactive? Well, this one is. And why do you think it's more reactive? All right. Well, it's more reactive because it's smaller. Okay, so the formal group is more electrophilic because of the lack of the alkyl groups. So if you have mixed anhydrides, your nucleophile is going to attack the least substituted group. Here's the ester synthesis. How do you make esters? You can make esters from everything. Carboxylic acids with the Fischer esterification, acid chlorides, anhydrides, trans-esterification. All right, we've also seen the diazomethane. So this is a good slide of showing you all the ways that you can make an ester. Okay. Now here's reactions with esters. You can make an acid, an ester, an amide, LAH it to the alcohol, add 2 Grignards to make the tertiary alcohol, or dival to make the aldehydes. Very similar to acid chlorides. Okay, here's a formation of lactone, an intramolecular Fischer esterification. Okay. Here's reactions with amides. You can hydrolyze, you can LAH it. POCl3 can dehydrate your amide to the nitrile. Right, here's a dehydration reaction. P2O5 works also. That's what I used to do these reactions in, but POCl3 is the more common one. So strong dehydrating agents can eliminate the elements of water from primary amides to give nitriles. Okay, again, formation of lactams, same as lactones, intramolecular. You actually just need a little bit of heat and you can do it. Beta lactams are interesting compounds. These are very common ones. These are types of penicillins. Okay, all these are types of penicillins. And the beta lactam is a 4-membered ring lactam. Specifically, it's called beta because it has only 2 carbons, an alpha and a beta. So I think that's why they call them beta lactams. Okay, and these are actually really good alkylating agents, which is why I think it works really well as an antibiotic. It alkylates the cell walls of cells, and it disrupts the synthesis of the cell wall of bacteria. So I believe that's how it works, and I think they talk about it here. But unusually reactive 4-membered ring amides are capable of acylating a variety of nucleophiles. They're found in an important class of antibiotics. So imagine your nucleophile right here as the growing peptide of your cell wall. Okay, everything's made of amino acids, and it attacks your antibiotic. Notice, what's that? Tetrahedral intermediate. That's your leaving group. Protonate. Your cell wall now gets attached to this complicated part of it, which then basically stops the synthesis of the cell wall. Okay, so nucleophile attacks the carbonyl of the 4-membered ring, forming a tetrahedral intermediate. The driving force is you have a 4-membered strained ring, right? It wants to pop open pretty easily. Okay, so here they actually start showing you how it, so here's the active enzyme. All right, this would be the enzyme that makes the bacteria, the cell wall of the bacteria, and it adds to one of these, and now boom, that's added on there, and now you have deactivated the enzyme that makes the cell wall. So the beta-lactams work by interfering the synthesis of the bacteria cell wall, basically by deactivating the enzyme that makes the cell walls. Okay. Synthesis of nitriles, these are all the reactions. This is kind of a good summary of pretty much everything that we've learned. It even shows you all the sections. So PLCl3, dehydrating agent, SN2 mechanism right here, diazomethane from chapter 19. Okay, this is one where you add the cyanide to the carbonyl to form the cyanohydrin. Reactions of nitriles. Okay, you can take a nitrile to an amide or to a carboxylic acid, LAH it to the amine, add a Grignard to the ketone, add dival to the aldehyde. Thioesters just have sulfur in it. Basically, whatever you can do with an ester, you can do with a sulfur. In fact, sulfur is more reactive than the oxygen. So you can make thioesters by just doing a similar type of Fischer esterification. Okay. It says the resonance overlap in the thioester is not as effective as is an ester. That's why they're much more reactive. So therefore, thioesters are more reactive towards nucleophilic acyl substitutions in normal esters. Okay, and here is coenzyme A. It's the structure of coenzyme A. You see this long, complicated structure, but basically this is the important part of it right here. Okay, so basically it works as a, it's basically whatever we're going to add to it, I'm sure it'll show you, is going to add to here. It kicks that up, kicks that down, and kicks that out. So the coenzyme is used as a acyl transfer group. Okay, hence the name, acyl transfer reagent. It's transferring an acyl group somewhere on a biological molecule. Okay, so here's the mechanism of action. Same thing, tetrahedral imine, it pops down, and you've acylated whatever your nucleophile is. Okay, whether it's a protein or a peptide or a DNA molecule or whatever. Okay. Carbamate esters and isocyanates, these are interesting compounds. Isocyanates have this N double bond, C double bond. All right, crazy glue actually is a type of an isocyanate. They react very reactive with OH bonds. If you have, if you've ever smelled crazy glue, you know, it kind of makes you tear a little bit. It's because it's reacting with the alcohol, and you actually form acid in the reaction. Okay, there actually is a little bit of acid that forms, so that's kind of what the burning sensation is when you do it. But here's an example of an isocyanate and 1-methanol to make a carbamate. This is called a carbamate, where you have a nitrogen, carbonyl, oxygen. Okay, so you can actually take, well, this is a carbonic acid, which is unstable, which you can turn it into an amine, just kind of a side reaction. Carbamates also make polymers. They're very common to make polymers. I'm sorry, that's a carbamate. This is a carbonate, polycarbonates. Polycarbonates are plastics, where a carbonate is where you have an oxygen, carbonyl oxygen. It's kind of a reverse of an anhydride, right? Remember, anhydrides are carbonyls, oxygen, carbonyls. This is the reverse, where you have oxygen, carbonyl, oxygen. And this is just an example of a polymer where you have many. So basically, you have this react here, and then you have that one react on another one, and another one, and so forth and so on. You see, you can have a squiggly line here, meaning it just keeps going on and on and on and on and on. Okay, so it's a type of plastic. Okay, you can also make polyesters this way, as well as polyurethanes. Okay, here's a polyurethane. Polyurethane is a carbamate. All right, see, it's a carbonate. And you take a diisocyanate plus ethylene glycol, and you can make a polyurethane. Foams are polyurethanes. They're also types of plastics. All right, so that's pretty much it for the chapter. Again, bring questions to lecture, but pretty much that it's the same mechanism over and over again. Organizing it like how I showed you is probably the best way to learn the reactions in this chapter.